Welcome to The Explainer. Today, we're jumping straight into the fascinating, Lego-like universe of organic chemistry. Seriously, if you look around right now, literally everything you see, touch, and even the very cells in your own body are driven by the rules we're about to unpack. We're going to explore how one single element can be responsible for an absolutely mind-boggling millions of different compounds. It's wild.
Okay, here's our roadmap for today. We'll start with carbon, the ultimate builder. Then, the language of chemistry, moving into shapeshifters and isomers, followed by electrons and reactions. After that, we'll open up the chemist's toolkit and finally look at the impact on our world. Let's get into it.
Section 1. Carbon, the ultimate builder. Obviously, we got to start with the absolute star of the show.
Which begs a pretty massive question, right? Out of all the elements on the periodic table, why is carbon so special? Why is this one specific element the undisputed backbone of life sciences, of the plastics in our phones, the fuels in our cars, and literally the DNA in our cells?
Well, carbon is the ultimate builder because of three totally unique traits. First up, tetravalency. That basically means carbon has 4 valence electrons, so it's always looking to form 4 stable covalent bonds to be, happy. Think of it like a connector piece with exactly 4 docking ports. Next, it can form multiple bonds, single, double, or even triple bonds with itself and other elements like oxygen. But the real magic, that's catenation. Now, catenation is just a fancy word for a really simple but incredibly powerful concept. It's carbon's ability to snap together with other carbon atoms. And it doesn't just form pairs, no, it forms endless straight chains, wildly complex branching structures, or these massive closed rings. This one property right here is the reason why millions of organic compounds can even exist. All right, section 2, the language of chemistry. So we've got our building blocks, but now we need the grammar and vocabulary to actually talk about them without losing our minds.
Imagine trying to name millions of unique Lego structures without any kind of system. It'd be total chaos. That's exactly why the IUPAC nomenclature system exists. It gives us 5 logical, exact steps to name any organic compound, completely taking the guesswork out of it. You just find the longest carbon chain, spot the functional group, number the atoms, identify any substituents, and finally write the name out alphabetically. So if those 5 rules are our grammar, these prefixes, they're our basic vocabulary. They tell us exactly how many carbons are in that main chain. Got 1 carbon? You start with meth. 2 carbons is eth, 3 is prop, and so on. So the next time you hear about methane gas or a propane tank, you'll know exactly how many carbon atoms make up the core of that molecule. Pretty cool, right?
Then we add functional groups. We take those carbon chains and attach these specific clusters of atoms. And these groups dictate exactly how the molecule is going to behave. It's basically like adding an action verb to our chemistry sentence. For instance, if you add a hydroxyl group, that's an OH, to an ethane chain, boom, you've got ethanol, which is an alcohol. The structure entirely dictates the identity.
Section 3. Shapeshifters and isomers. Let's look at how these pieces physically arrange themselves. Because in organic chemistry, shape is literally everything.
At the most basic level, we classify open carbon chains into 2 main camps. On the left, we've got saturated compounds, like alkanes. These are totally maxed out, containing only single bonds. But on the right, we have unsaturated compounds. These guys contain double or triple bonds, meaning they actually have the capacity to bond with more atoms if those multiple bonds ever get broken open.
Which brings us to isomerism. This is honestly such a mind-bending concept. You can take the exact same molecular formula, let's say 4 carbons and 10 hydrogens, C4H10, and build completely different molecules. If you build it in a straight line, you get N-butane. But if you branch it out, you get isobutane. Exact same atoms, totally different structures, which means they have entirely different physical properties, like boiling at completely different temperatures. Moving on to section 4, electrons and reactions. We've built the molecules, named them, looked at their shapes. Now, let's see what happens when we intentionally smash them apart and force them to react. You see, chemical reactions are all about breaking old bonds and making new ones. When a covalent bond breaks, which is really just a shared pair of electrons, it happens in one of 2 ways. It can split fairly, that's homolytic cleavage, where each atom takes 1 electron, creating these highly reactive things called free radicals. Or it can split unfairly, heterolytic cleavage, where 1 atom just hogs both electrons, creating positively and negatively charged ions.
So once those bonds are broken and the electrons are moving around, the pieces have to recombine. And there are 4 primary ways they do this to create brand new substances. Substitution is exactly what it sounds like, swapping one piece out for another. Addition is attaching new atoms across those unsaturated double or triple bonds we just talked about. Elimination is the exact reverse, removing atoms to form multiple bonds. And rearrangement, that's an internal shapeshift, where the molecule just reorganizes its own atoms.
All right, Section 5, the chemist's toolkit. Now, all this breaking and combining is happening at a microscopic level. To actually observe and use these reactions in the real world, chemists need a highly specialized toolkit.
Because when you run an organic reaction in a lab, you almost never get a 100% pure product right off the bat. You get a messy mixture. So chemists rely on essential purification techniques like sublimation, crystallization, distillation, and chromatography to isolate the exact organic compound they're after.
Sublimation is a particularly cool party trick for very specific solids. Most things, they melt into a liquid before boiling into a gas, but some substances, like camphor, completely bypass the liquid phase when heated. They jump straight from solid to vapor. Chemists use this to isolate them super fast, leaving all the gross, non-sublimating impurities behind.
Once they've purified it, the chemist has to analyze their creation to confirm what it actually is. They define it in 2 ways. They use qualitative and quantitative analysis to find the empirical formula. That's the absolute simplest ratio of atoms. But to really know the full scope, they use math based on mass to scale that ratio up to the molecular formula, and that tells them the actual, literal number of atoms in a single molecule. Which brings us to our final section, number 6, impact on our world. Let's zoom out from the lab for a second. We've seen the microscopic rules, the grammar, the purification, but how do these chemical Legos actually shape our macroscopic reality?
The truth is, you're interacting with organic chemistry every single day, probably without even realizing it. Whether you're dressing a salad with vinegar, which is an acetic acid solution, taking off nail polish with acetone, or filling your car with methane-derived fuels. From everyday solvents to life-saving medicines, these carbon compounds are literally the invisible architecture of modern society. But we have to admit that massive footprint comes with serious consequences. These compounds give us miracles like antibiotics, sure, but they also create monumental problems like enduring plastic pollution. That's exactly why the principles of green chemistry have emerged. It's a huge push to make this science sustainable, designing reactions that prevent waste, use safer solvents, require less energy, and rely on renewable raw materials instead of fossil fuels.
And that leaves us with a really critical thought to wrap up on. We've mastered the rules of carbon. We know exactly how to break it, shape it, and build with it. But with organic chemistry driving both our greatest modern miracles and our most pressing environmental challenges, how will we use this ultimate builder to design a cleaner, more renewable world? Thanks for joining me on this explainer. Keep questioning and keep exploring.